Our next algorithm has a wonderfully geometric idea. It's the support vector machine. Imagine separating two groups with a line. Many different lines would do the job. The support vector machine asks a sharper question. Which line is the safest? Here are our two groups again, with a clear gap between them. Look, this line separates them. So does this one, and this one. Every one of them gets the training data perfectly right, but some pass dangerously close to the points. The support vector machine picks the line with the most breathing room on both sides. Think of it as the widest possible street you can drive between the two groups. The center line of that street is the decision boundary, and the width is called the margin. Here's the surprising part. Only the points right on the edge of the street matter. These border points are called the support vectors. They alone hold the boundary in place. Move a point far from the street and nothing changes. Move a support vector, and the whole boundary shifts. Why the widest street? Because a wide margin leaves the most room for new, unseen points. A boundary crammed right up against the data is fragile. A slightly different new point could fall on the wrong side. The widest margin generalizes best. Real data is rarely so tidy. Often a few points stray onto the wrong side. So the support vector machine allows a few violations in exchange for a wider, sturdier street. A setting called C controls that trade-off, how strict to be about the stragglers. But what if no straight line can separate the groups at all? Picture the safe customers forming a cluster, completely surrounded by risky ones. No single straight line can wrap around the middle. We seem stuck. Here's the clever escape, called the kernel trick. We lift the points into a higher dimension. Watch this line of points, red in the middle, green on the ends, no single cut works. But lift each point up by its distance from the center, and suddenly a simple straight line slides right between them. Support vector machines shine when the classes have a clear margin, and even when there are many features. The costs: they need scaled features, they slow down on very large datasets, and the kernel version is hard to interpret. Still, for the right problem, that widest street is a beautiful idea. In scikit-learn, it's the SVM, the support vector classifier. We pick a kernel, RBF is the popular curved one, and set C, the strictness style. Then the same fit and predict. Just remember to scale your features first. So a support vector machine finds the boundary with the widest margin, defined by a few support vectors. And the kernel trick lets it curve, by lifting the data into higher dimensions. Next, an algorithm that reasons with probabilities instead of geometry, naive Bayes.